to my talk, I'd like to tell you about a measurement study looking at the Google Dialer and Messages apps on Android. There's been a good deal of interest in the privacy of Android apps, but far less on the system apps themselves. So in this study we look particularly at the Dialer and Messages apps, which are core system apps pre-installed. The Dialer apps used to make and receive phone calls, and messages are used to send and receive SMSs and other messages. So these are pre-installed system apps. Difficult to use the phone at all for anything without using these apps. They're core parts of the system. And the interest is what data, these are Google apps, what data are they sending to Google? Our setup's straightforward. We take a phone, do a factory reset to get a clean setup. During onboarding, we say no to all the questions asking us to say secure data. So that's mimicking a privacy-conscious user, but who's busy then doesn't later drill down to the settings and change anything. So when asked, says no, but otherwise doesn't do anything else, and then makes and receives calls and texts. We intercept the traffic, do a man-in-the-middle attack using pretty standard methods, and so we can see the traffic. But that's actually the easy part. The traffic is binary encoded, and understanding the content is the tedious, time-consuming part. That's the bulk of the work for this study. A quick preview of the results is that both of these apps are sending detailed usage data to Google servers. What do I mean by usage data? So the screens viewed and when, so time histories of app usage, when interesting events happen and what those events are, time and duration of phone calls, when messages are sent and received, hashes of the message text, which potentially allows the sender and receiver in a conversation to be linked, the duration of phone calls plus a timestamp, which again can be potentially used to fingerprint phone calls and allow both ends of a connection to be linked. By default, the phone numbers involved in the call are also sent. That can be disabled. All the other measurement I'm going to talk about cannot be disabled. There's no opt-out from it. The only one is this. This transmission of phone numbers is related to call blocking service, so it can be opted out, but it's opted in by default. The data collection isn't anonymous because the Google Android ID is sent alongside it. Most of the data, or for the Firebase data, the Ad ID and a Firebase ID is sent alongside it. I'll explain those identifiers shortly, but they're linked to the Google user account, and so generally to the user's real identity, and they're not you can't reasonably be called anonymous. There's no opt-out, there's no consent, there's no public documentation, there's no app-specific privacy policy. So it's not a great situation. These measurements were all taken in Europe using handset spot in Europe, so that the behaviour might be different elsewhere, but there's no evidence suggesting that from the measurements we've taken or the inspection of the code that we've carried out. And we're not going to go down a legal analysis of what's going on here, but I'd like to bring up the three legal basis for data collection, because they help to think about the privacy aspects. One is data can be collected if it's anonymous, so it can't reasonably be linked to a real person. That doesn't apply here because of the way the data is tagged with the Android ID. If informed consent is obtained, but there's no consent sought or given in this case, and so presumably Google are relying on this last basis where it's for legitimate interest for some specific purpose, which we don't know because they don't tell us. Whether it's necessary for that purpose, we can't comment on that because we don't know the purpose. And balanced against interest, again, we can't comment on any of that because there's no information. Another important thing to bring out here, I think, is the role of Google Play services in this setup. So these are Google apps running on a Google ecosystem. They don't send data directly to Google. They send it via Google Play services and through two APIs. One is a private API, which is called the Clearcut Logger, and it sends it to a log batch endpoint, and the other is Firebase Analytics, which is a public API, and then it sends it to appmeasurement.com, which is our Google domain. And the Google Play Service is a highly privileged app on handsets, and so this data that's sent by the apps is enriched by Google Play Services with identifiers. The Android ID isn't immediately available to this app, but it's added to the data by Google Play services. And similarly, there's a cookie added, NID cookie added, and authorization headers linked to the user account are added to the data by Google Play services. So it's, in a way, it's elevating the privileges. It's adding data that's not available to the app, tagging data with information that's not available to the app, but is available to Google Play services. And so let's look at these identifiers a bit more, because they're quite important, I think. One is this check-in connection isn't new. It's not new from this study. It's known already. There's some Google documentation on it. It's nearly the only connection that has Google documentation, because it's so many sensitive identifiers. It has this NID cookie that we'll see again and again. The IMEI identifies the SIM slot. It's got the hardware serial number for the handset, and it's got this Android ID. And these are linked together. And if we do Google Takeout for the user account, it's also linked to the Google user account. Then we can see these identifiers all being echoed back. So these identifiers really are collected and linked to the user account. That's not speculation. And so this is the flow that's happening. The data is being sent to the clear-cut logger, which is all that data is tagged with the Android ID, which is linked through that check-in connection we just saw to the hardware serial number and the SIM IMEI. It's also linked to the Google user account, which in turn will often be linked to your phone number and your credit card details if you make any purchases. And so that's linked to a person's real identity. So it's linked to the handset, linked to the person's real identity. And the Firebase data is tagged with a Firebase ID and a Google Ad ID. Now the Google Ad ID is linked to all the other advertising data that's collected from the handset, and so the data that's collected from the dialer and messages can be linked to all this other data that's collected for advertising purposes on the handset. And the Firebase ID is linkable to the Android ID because they're sent together in the same connection. Now whether the linkage really happens we can't say, because there's no documentation, but it's certainly possible. So the bulk of the work in this study was actually decoding the data sent. This is the structure of, I will only look at the clear-cut logger data here because it's the most important. The paper itself discusses Firebase. So it consists of different log sources all batched together. Each log entry consists of a header and then a set of log entries from that log source. The header contains a Google Android ID and this NID cookie, which are linked to the user account. Here's a typical Google Dialer log entry. You can see it's not particularly informative. You see numbers. We don't know whether they're sensitive. We don't know what they mean. And so the work is to figure out what they mean. So we need to track down the code that generates these messages and work backwards and find out what these values really represent. And when we do that, this message changes to be the one on the right here, which is the decoded version. So many of these values are referred to enumerated types. So the 2 there tells us this is related to a message. The 1 here tells us it's related to the event that message has been sent. And these numbers at the bottom turn out to be hashes of the messages. And so with that in hand, we can go make and receive, send and receive messages and see what information is recorded. Now this is a summary. Each of these events has all that other baggage attached to it. I've just extracted the event name and some relevant data to try and compress it all and make it easier to digest. So this is the sender. You can see a message being created, it being composed. This is a suggestion as to who to send the message to. And then the message finally gets sent, and here's a hash of the message and the hash of the previous message. These are all sent to Google. Receiver side, the message is received. That event is recorded. The hash of this message and the previous message are sent to Google. There's the UI events are logged, the notifications displayed, that the user clicks on that and launches the app, and then that the message is viewed as displayed and read by the user. So there's details of the user actions are sent to, fine-grained detail of the interaction with the app are sent to Google. Message hashes are sent to Google, allowing linkage. You see it's the same hashes on both sides. And this data collection can't be disabled. There's no documentation. It's all linked to the Google user account via the Google Android ID. This extra part here at the bottom is Firebase. Sorry, not Firebase, it's a separate log source, also sent through ClearCut, also linked through the Android ID from the call blocking service, and it sends the phone number, the incoming phone number. And by default that's enabled. Firebase logs the event of a message being sent and a message being received, and links it to the advertising ID and this Firebase ID. Again, can't be disabled, no documentation. And now a dialer is much the same. I could go through the dialer, but essentially the level of logging is very similar. The fine-grained information on user interactions with the app, essentially call fingerprints that allow linkage of both sides of a call, and when the call blocking is enabled, as it is by default, then the incoming number, and it's all tagged with the Android ID for the ClearCut stuff, or the advertising ID and the Firebase ID when the receiving and sending events are recorded through Firebase. So the setup's very similar. So just to summarise, we all know Google's an advertising company, so it's interested in data. Data is part of what this thing about users, to profile them and understand them better, to help target adverts, and that's the core business for them. They have large software SDKs that are included in many large numbers of Android apps. Firebase, Google Analytics, AdMob, and so on are very common in third-party Android apps. Google, perhaps unsurprisingly, instruments its own apps. And not just dialer messages. Since this work, we've looked at other apps, and for example, Gboard does something similar. That's the Google Keyboard. I think the important takeaways here are, however, this data collection is done silently. There's no documentation, no opt-out, no consent. It's not anonymous. The Google Android ID is linked to the user account, and for most people will be linked to their real identity. It'll also be linked to your advertising ID, and yet there's been no consent sought for that. The data collected isn't boring, it's sensitive. It's things like message hashes and phone call fingerprints and fine-grained app usage data, which can potentially be used to profile a user. And these measurements are all taken with privacy-conscious handset settings. So these are baseline measurements, and more data might be collected under more normal settings. Most users will have less privacy-conscious settings. And I think it's a call to action, this work. Let me just make a comment at the end, that we need to be taking more measurements of this sort. We wouldn't know about them if we hadn't carried out a measurement study like this. Google certainly aren't telling anyone. And how else would you know? And yet users need to know these in order to help them make informed decisions. Policymakers and regulators need to know about them so that they can do their job, and technology developers need to know about them. People like Samsung are choosing to install the Google Dialer. They don't have to. Previously they installed the Samsung Dialer, which should behave differently. And so, but they don't. They're not aware of this data collection being carried out either. So this is just a small study that scratches the surface. I think there's, as a community, we should be doing a lot more of this to help, have real impact for a lot of people. Thank you.
Hi everyone, I'm honored to have the opportunity to speak in this conference. I come from TSS Lab in Beijing University of Posts and Telecommunications. The title of my presentation is Detection and Privacy Leakage Analysis of Third-Party Libraries in Android Apps. I implemented a tool named LibMonitor. Next, I will introduce from this aspect, include my research background, my technique, detail of TPL detection, and privacy analysis, evaluation, and conclusion. First, I will introduce my background. Today's apps require many additional functions to assist, such as user portrait, personalized recommendations, to cover the ever-increasing demand for app development. Developers on the Android application integrate TPL into their apps. TPL may collect user information to achieve their functions, but sometimes they may collect unauthorized or unnecessary data. For example, TPL provided by Atomic and Baidu have been exposed to security vulnerabilities. They secretly monitor users' behaviors and upload sensitive information to remote servers. However, there is no official unified management platform for closed-source Android third-party library. Besides, code obfuscation techniques also bring challenges to detecting TPL. Nowadays, users pay more and more attention to the protection of personal information, so it's important to detect the TPL in apps and perform privacy analysis. Part 2, I will introduce the technique of lead monitor. We propose a feature matching approach for detecting TPLs. First, we divide Android APIs into 50 categories according to their function, and then we extract API call frequency for each category as features. Then we perform fuzzy match to cluster feature vectors, and finally, we can detect TPL by cluster prediction. Our approach can resist code obfuscation, especially data code removal and control flow randomization. For the privacy analysis, we use dynamic instrumentation. During the runtime of application, we use dynamic instrumentation to monitor source and sink APIs. Then we perform information match and call stack analysis. Dynamic instrumentation can be easily applied on most sensitive interfaces like logcat, network, message, and clipboard, and so on. Part 3, I will talk about details of TPL detection. This is a flow diagram of TPL detection. First, we collect a large set of applications. Then we perform feature extraction. This feature vector will be clustered into lots of clusters. For a test APK, we will do the same operation of feature extraction. At last, we will perform cluster prediction to confirm which TPL is in this test APK. And in this section, feature extraction, we will group Android APIs into 50 categories according to the functions of them. We will pass text file in an app and count the call frequency of each type of API for each class in the app according to our algorithm. This is algorithm 1. The input of it is text file and AT. AT is the array that maps an API to its API type, in total 15 types. And the output is a dictionary containing feature vector and class name. First, the dictionary is initialized. Then we traverse all text files to pass and construct the text objection O. For each class C in objection O, we will extract CNAME and feature CF to dictionary. While the CNAME is not root dictionary, we will add the feature vector of CNAME to its parent dictionary. In this way, we can get features of all dictionary and classes. The next is feature clustering. For feature preprocess, we filter the feature vector data to remove this invalid feature vector. Then we normalize the feature vector data. After that, we use the bulk algorithm to cluster this data. We build the map between a cluster label and a TPL according to the package name. The next is cluster predictor. After feature clustering, we can get lots of potential third-party library in our cluster model. To detect TPLs in a single app, we first extract its features and normalize the feature vector in the same way as section before. Then we conduct a cluster prediction based on the models established in the clustering process. According to the map between labels and TPLs, we can get a list of TPLs used in the single app. Then is the privacy analysis. As can be seen from the picture, we use ADB and instrumentation of the source APIs to obtain device-related information. Meanwhile, we monitor source API and sync API to get a monitor log. A TPL list can be obtained from TPL detection. Then we perform information match and call stack analysis to get a report of privacy analysis of TPL. In this section, PIL collection, we can use ADB and instrumentation of the source API to obtain device-related information. Considering that an app may encrypt or encode the device information when transmitting it, we preprocess acquired device information using common encoding and encryption algorithms, such as base 46 SHA-1. And finally, we can process the information list PIL. In this table below, I list some ADB command to get device information. Next section is dynamic instrumentation. We use a tool named Frida to perform dynamic instrumentation. It's composed of an Android device and a PC-side controller. The device is installed with Frida server, and the PC-side controller is implemented as some scripts in JavaScript, which are injected into the Android device. We use Monkey to simulate the user's operations on the app. During the app's execution, the scripts will record the running log for the later analysis. Next, in this section, we match process information list with logs. For the logs of Sync API, we just match logs with TPL directly. For the logs of source APIs, as long as the source APIs are called, we define that the private information is matched, but with low risks. Device information is generally a specific string, so it can be matched directly in the monitor log. And for the user-specific personal information, it has a certain format, so we can use regular expressions to match it. Next section is call stack analysis. As long as the privacy information is successfully matched, we will evaluate the privacy leakage risk of TPL by passing the call stack. We divide the privacy leakage risk of them into 4 levels. Level 0, so no private information is matched. Level 1, any TPL calls a source API directly or indirectly. Level 2, Any TPL indirectly calls a sync API, and any private information is matched in the API monitor log. Level 3. Any TPL directly calls a sync API, and any private information is matched in the API monitor log. Then is the evaluation. We get an app dataset from a public dataset which contains a ground truth of TPL in apps. Our dataset consists of two parts, that is dataset OB and dataset PER. We compared our tool with LibRadar and libd. We designed experiments to answer these three questions. First question: how is the link monitor's capability to resist obfuscation? To evaluate the capability of resist code obfuscation, we perform TPL detection on dataset OB with 162 apps, which are obfuscated by ProGuard and -O. The results are shown in the table. We can see that the link monitor has best performance on F1 matrix. LibRadar performs well for ProGuard apps, while libd perform well for -O apps. Question 2. How does the link monitor perform on detecting TPLs? To measure the precision of TPL detection for real-world application, we use dataset PER for evaluation, and the results can be seen in the upside table. This result shows that link monitor outperforms other tools on F1 matrix when detecting closed source TPLs. Question 3. Is link monitor efficient compared to other tools? To evaluate the efficiency of link monitor, we run it on two baseline tools on dataset PER. The experiment results are listed in the table below. The performance of link monitor is significantly better than libd and slightly weaker than libradar. Then we perform privacy leakage analysis on 64 apps and obtain the following results. First, these are some case studies in our experiments. Some apps may leak private information through interface other than the network interface. For instance, as shown in this picture, Cutler app outputs advertiser ID information through Logcat interface. It's marked in red. Besides, we found a serious security risk in DoorDash app. It transmits the password and the email in plain text, which means that we can see users' password and email in Logcat. That's our experimental results. We define a piece of privacy leakage data that one TPL participated in as a privacy leak risk. For example, if a privacy leakage behavior involves two different TPLs, we will judge it as two privacy leakage risks. Link monitor found pieces of privacy leakage risks. These risks are listed in this table. We can see that the Google GMS is most used. We also record the type of private information that are leaked more frequently, and the advertiser ID is the most easily leaked type of private information. Besides, we count the frequency of source APIs and sink APIs called in these privacy leakage risks. That's the result of them. That's sink API and that's source API. And last, I want to talk about the limitation of Leaf monitor. First, Leaf monitor can also detect open source TBLs, but it can't accurately identify the specific version of each TBL. As a future work, we will combine clustering method and similarity comparison method to address this issue. Second, our approach to analysis private leakage can obtain the complete data flow from source to sink, which needs to be improved in the future work. That's all. Thanks for your listening.
Hello everyone, I'm Spandan Mahadevegowda and the work that I'm presenting today is secure CV2X using commercial off-the-shelf smartphones or the LTE infrastructure. The work is supervised by Dr. Ryan Gerdes, Dr. Thirapat Chantam and Dr. Rosu, and we are a collaborative group from Virginia Tech and Utah State University under NSF Aspire. Starting off with a small outline of today's presentation, I begin with some background and introduction for this work. Then we look at the system, network and threat models, following which I describe our secure CV2X framework. Consequently, I'll cover the evaluation of our framework and finally summarize with a conclusion. So let us start with some background, motivation and understand the challenges we are trying to address. We know that over the last few decades, with the ever increasing electronics in vehicles in terms of sensors and computational power, and now the electrification of the automotive infrastructure, the industry is stepping up to provide complex features like automated driving, advanced driver assistance, enhanced multimedia, etc. However, this requires connecting vehicles and the surrounding infrastructure and the power grid via intricate communication networks, leaving us with challenges as with any new advancements. One critical challenge is time constraints required for information exchange to have any relevance for safety applications, and two, to protect the integrity of this information, especially from new attack vectors due to added communication interfaces. Just to shed a light into the matter, prior works on Jeep and Tesla have shown that new attack surfaces can be compromised to pose threat to both life and property. One such popular connectivity framework is the Cellular Vehicle to Everything or CV2X framework, wherein we need to find a solution to securely exchange data over the cellular network between the vehicles and the infrastructure, have negligible processing overheads while doing so, meet the latency requirements to ensure safety in applications like driver assistance, smart lane change, collision warning, etc. And finally, reuse existing infrastructure as much as possible. Opportunely, given the penetration of cellular technology, the already established physical infrastructure and the network coverage, plus its advantages over other vehicular communication frameworks like DSRC, we propose to use commercial off-the-shelf smartphones as secure CV2X radios while not compromising on their original functionality to enable and adopt cellular vehicle to everything. Since the infrastructure is already available and smartphones are omnipresent, only a secure CV2X application would have to be installed by the users to enable CV2X. It is also important to note that our idea makes use of an intermediary server to connect the UEs instead of direct protocols to encompass a larger smartphone user base. And to understand the framework better, we always analyze the idea considering both the UE and the network. Specifically, the processing and security aspects of the UE to have negligible processing overheads and protect data integrity, and then the bandwidth and latency aspects of the cellular network so that we meet the time constraints for critical automotive applications which involve the safety of users. To understand the latency constraints for safety applications, given their criticality, the European Telecommunications Standards Institute and Department of Transportation have outlined requirements by classifying important V2X application scenarios, mostly periodic with a select few event driven. Here is a table that outlines these applications, and as seen, 7 of these applications have a deadline of 100 milliseconds or more, while only pre-crash sensing mandates 20 milliseconds. So in our work, as preliminary analysis of using LTE, we target the 100 milliseconds constraint and evaluate the same. Now to understand what is exactly exchanged between vehicles, we have a look at basic safety messages or BSMs. These are ASN1 encoded messages specified in the SAE J2735 specification for V2X applications. For our work, instead of using different messages for different applications as in the table, we use the standard BSM that carries the vital information of the considered vehicles. The BSMs in our case contain information about the vehicle's position, its speed and direction, and a few other parameters. Now let us see the user and system, the network configurations, and the threat model for our work. Starting off with the user end devices or smartphones, we have the smartphones connected to the vehicle on one end and the CV2X server on the other. These smartphones of today are powerful in terms of processing power and contain security extensions like ARM Trust Zone that can provide explicit code, memory, and peripheral boundaries between the secure and non-secure domain. We make use of this security extension to deploy a secure CV2X application over a trusted execution environment to exchange GPS and vehicular information in the form of basic safety messages or BSMs. Each UE would send a BSM periodically to the CV2X server, which is receiving similar BSMs from other UEs. The server then filters and responds back with a payload of relevant BSMs back to each of these UEs. For the network, we consider 4 topologies. First is a very standard setup with no changes to the LTE infrastructure, that is, a server on the internet or the public data nodes, albeit with the condition that the server should be on a prioritized network and also in geographical proximity of the ENVs. Then, the configurations focus towards moving the server closer to the end user to eliminate additional round-trip latency. As seen here, we move the server to the end of EPC and eliminate the latency over public gateways and the internet. Then we consider having the server as a component of the EPC or a subsystem of the EPC. However, this configuration would require significant changes to the existing LTE architecture and its specifications. So in this work, this topology is not considered. And finally, we move the server as close to the end user by having it at the towers or ENBs. The idea is to have a computationally powerful server at one ENB and have other ENBs within a given geographical locality share it. Probably via backhaul wired connections or the X2 interface. However, for simplicity, in the current work, multiple ENBs are not considered. Now moving on to the threat model, we consider that the attacker can remotely gain access to the UEs via cellular internet or any other short-range wireless interfaces. Once the attacker has remote access, we consider that the attacker has complete control of the non-secure kernel. As the LTE modem and GPS module are shared between the CV2X application and other standard smartphone applications, the attacker can corrupt or replay data to threaten the safety of passengers by providing wrong information for the safety critical applications. Or they can just bombard the modem and the GPS module with requests to cause a denial of service. Additionally, for our work, we do not consider any attacks that require physical access of the UEs and assume the complete integrity of ARM Trust Zone and the trusted execution environment, which is OPT in our case. Now, let us look at the actual implementation and details of the proposed framework. Here, I present an overview of the secure CV2X application. The user connects the UE to the vehicle and starts the CV2X application. This triggers an interrupt on the secure side via the secure monitor to start the CV2X trusted application, or TA in short. The TA establishes a secure connection to the vehicle and then starts the internal secure timer. The TA builds the BSM payload every 100 milliseconds using data from the GPS module and sends the data to the server over the LTE modem. The reply from the server, which is BSMs from other vehicle smartphones, is then received and processed to issue commands or warnings to the vehicle. In case of any discrepancies, the TA invokes a threat action function to take over the modem and GPS module to re-establish broken connection or resolve issues and run the CV2X in safety mode. The user can stop the application once the commute ends. In case of when the CV2X application has switched to safety mode due to a detected discrepancy, the user would have dedicated physical buttons on the UE which the attacker does not have access to stop the application. Now moving on to the secure data that is exchanged, we look at the BSM payload in detail. We have a message type field that specifies the type of BSM payload. For our work, we keep this constant. The next field is a key ID since we use rotating keys for our HMAC computation and in order to improve robustness against brute force key extraction, following which the IMEI of the UE is appended for the server to identify the UEs without having to query back to the HSS or the EPC of the LTE core network. Then we have a length identifier since the BSM packet can vary in size, and the BSM payload itself, and finally a timestamp that is used as nonce for the HMAC. The HMAC for this whole packet is then computed using a lightweight hashing algorithm called the ASCON hasher and then appended to form the final payload that is sent to the server. The final payload from each UE is about 120 bytes. The server would verify this HMAC using the key ID present in the payload, and valid data would be filtered and forwarded to relevant UEs. In case of threats, as discussed in the threat model, the attacker can compromise the LTE and GPS components to disturb the CV2X communication. So here we look at how the threats are detected and managed. Starting with the data corruption of the received payloads, the HMAC verification would fail. Similarly, if the attacker overcomes the HMAC gateway by using saved data to have replay attacks at a later point of time, the timestamp or nonce can be used to check for data freshness. The attacker cannot just edit the timestamp to overcome this, as he cannot compute the correct HMAC for the modified data. And finally, if there is a denial of service on the modem or the GPS, the internal secure timer can also be used as a watchdog. In all three cases, the secure side would switch the UE to safety mode and explicitly hand over control of the modem and GPS module to the secure side. This cuts off access of the modem and GPS from the attacker. Though the mitigation strategy is strict, here it is essential given the safety of passengers. One other attacker scenario not discussed in threat model would be the possibility of compromised user input to stop CV2X application. However, the mitigation strategy is very simple. Only general purpose input-output connected to physical buttons on the UE, which the user has access to but not the attacker, could be programmed to stop the CV2X application. Now moving on to the evaluation and analysis. We start by taking a look at the various overheads and latencies involved in our framework. First, the time taken to request and retrieve GPS information, then use this data to build the payload, send the payload to the modem, which is sent to the server, followed by the network round trip delay, which varies based on the different topologies that we discussed earlier, and the processing overhead for filtering and validating data packets on the server, receive this data from the server to the modem and then load it to the processor, extract this payload and validate it, and then send relevant commands or warnings to the vehicle. For the implementation, as we are evaluating the latency measure, we have a server that receives data from the UE and responds with random but valid HMAC verifiable BSM packets. And this is done on an open source ARM phone called the Pine phone. For server on the internet, the phone is connected to the AT&T Twilio LTE network with an AWS server running the CV2X application server approximately 27 miles afar. We measure the latency across urban, semi-urban and highway terrain with varying vehicle speeds between 20 to 60 miles per hour. For server at the end of EPC, we create a private LTE network with custom SIM cards and a USRP B210 with open air interface software stack and run a standard 20 MHz LTE FTD configuration. The ENB and EPC plus server are set up on individual PCs as described here. For the server at the end of ENB, we modify the above private network and integrate the MEC middle box work to implement an edge server at the ENB, which acts as a filter between the ENB and the actual LTE core network, wherein it filters standard LTE data to the core network but the CV2X application data to the CV2X server. Coming to the hardware setup results, we split the evaluation into UV processing and internal communication overheads and the network round trip delay. Here in table 1, we see the various measures for different processes involved in getting the GPS information, building the payload, and communicating with the modem or the GPS module. In the case of receiving relevant BSMs of other UVs from server, we measure the overhead for 1, 5, and 10 BSMs. Since each payload is about 120 bytes, for 10 BSMs we are over 1 kilobytes of data. And as seen, the total overhead considering the worst case is about 11 milliseconds when 10 BSMs are received for every BSM sent. We do measure the overhead for GPS fetch separately in open skies as it is not feasible to obtain GPS signals within the lab setup. For round trip delays, we see that the AWS server plus AT&T Twilio network does meet the required 100 milliseconds constraint, but this is marginal as we need to have buffer for unexpected delays in the case of safety critical applications. For latency, in the case of server at end of EPC and server at end of ENB, we have better results and space for considerable safety buffers as well. Note that in the case of server at end of EPC, we only measure the ideal case of having the server right next to the EPC and negligible channel delays between EPC and ENB. Additional latency would be present if the server is far from the EPC. So theoretically, for server at end of EPC, the latency would be between server on the internet and server at the end of ENB cases. Then, to extend our analysis further, we use NS3 simulation considering multiple UVs within the network. This is to find the upper bound of the number of UVs that can be supported for a given threshold latency. This is for the most favorable network setup of having the server at the ENB. The simulation considers a standard 20 MHz FDD setup with 2x2 MIMO antenna or multiple input multiple output antenna on the ENB. In the above graph, we have a number between 45 to 50 UVs with a threshold latency of 60 milliseconds considering safety time buffer and processing overheads for the BSMs. In summary, with this work, we demonstrate and provide a proof of concept work to implement a secure CV2X framework on commercial smartphones to mitigate data corruption and replay attacks. We also consider denial of service attacks. Then we analyze and evaluate the framework with the discussed network configurations to show that the proposed framework has negligible processing overheads, albeit with some operating limitations. The results indicate that a secure CV2X framework can be adopted using commercial off-the-shelf smartphones, thereby eliminating the need for dedicated CV2X modules. We do have some limitations, which we discuss further in the paper, together with additional future avenues in research. And finally, thank you for your time, and if you have any questions, please do reach out to me at the following email.